Today's webinar is on safety critical design, and as part of that, we'll touch on a few tools from Graphics, including ReqTracer, Covercheck, and SecureCheck. So we'll start out with just a little bit of a safety critical design overview. Then we'll talk about requirements tracing with ReqTracer. We'll talk about coverage closer and how to make sure you've tested everything. And then we'll have a section about SecureCheck, which is a formal verification tool that we have for basically making sure that your hardware has no backdoor paths into it, etc. And if we have any time at the end, depending on how fast I go through things, I might talk a little bit about the black domain crossing tool. So safety critical design overview. Basically, safety critical design is all about trying to make sure that you have designed to your requirements documents, that you have implemented all of those requirements, that you have tested all of the requirements in your design, and that you can prove it. This slide is basically giving you some of the problems that can come up if you're not following a structured safety critical design process. So it's just kind of an overview there. So if you think about that ad hoc process, usually you have an idea, start implementing code, you implement the code, you do some minor testing of the code in simulation, and then a lot of times, it's let's get it into the lab as quickly as possible. And then once you get into the lab, it can be difficult to make sure that you have tested and all of the requirements and that everything is working. So a more structured process is that you have the idea, but then you spend some time doing planning, you do a good requirements document, you do a good testing plan. So there's a bit of upfront work in the planning, but because you can do that, you can then be doing the code implementation and the verification. Those tasks can kind of go on in parallel. If you've done a good verification, then usually the lab bring up is a lot quicker. There's a lot less surprises in the lab, and you don't get into what we call the lab trap. So a structured process is basically adopting some of these best practices. This process really started with the DO254, which was a standard for designing programmable logic in the aerospace world. That process has broadened to include banking, to include the ISO 26262, which is an automotive standard. There is an equivalent standard for the FDA. There's an equivalent standard for many different industries now, and they're all very similar. So that safety critical design process, like I said, starts out with a lot of pre-design, the planning, creating requirements, maybe doing a high-level conceptual design, and then over here on the verification side is that you create a set of tests to test your design. You're doing code coverage to make sure that you're coding everything. And then in the middle here is the requirements tracing. So it really starts out, as I said, with this planning document. So a good planning document is like the blueprints for a house. It is really saying exactly what's going to be done and making a lot of the decisions up front as soon as possible. So you really need like a system overview, all the documents. You need to say what the team is, what everybody's responsibility is going to be, an overview of the hardware, oftentimes the life cycle and the data of the project, what's going to live in there, and then setting out a schedule with milestones and reviews and audits. And oftentimes in these safety critical standards, like ISO 262 and DO254, there are third-party outside auditors who will come in and audit the project to make sure that all of these goals are in place. Planning document, oftentimes you want to make sure you have a unique part number. You want to have some kind of revision control on that document. As I said, you're going to have the approvers who approved and what kind of sign-offs do you need on this project. You're going to have a revision history of the document. Always wants to have a table of contents. You're usually going to have the first section will be a purpose and scope of the document, team members who are going to be involved, and then a functional description of both the architecture of the design, all the different design phases you're going to spell out, the verification activities. Then after all of these things, we get into declaring the requirements for that design. And this gets into creating those requirements in the document, showing how those requirements are implemented, showing how those requirements are tested, and then the code coverage to prove that you've tested everything. So oftentimes the requirements, depending on the complexity of the project, may follow this what we call a V diagram, where we start at a high level, break down maybe from the system level to the hardware level to the subsystem level to the module level, etc. So these requirements, each requirements document feeds off the previous level, and then the verification, you do verification at each level and match up that verification between each level. So design assurance is really like what it says. It is trying to prove that the design performs the intended function. The intended function is set up by requirements, and then for a requirement, first of all, you need to capture all of the requirements. You need to review all of the requirements. You need to manage the requirements through the project, and then you need to trace those requirements from level to level and from implementation to verification. So what is a requirement? It is a capability, a condition of the design that you're trying to solve or implement. It is a specification of what should be implemented, a description of the behavior. So really the requirements are the expectations that the person planning this system has in their mind. And the trick is to turn that knowledge into a written set of requirements. And when you have requirements, you need to make sure that they are complete, that they are correct, that they are implementable, that they're actually necessary, maybe that they're unique. You might have a priority on them, what's more important than other things. So those can all be part of a requirement. So the anatomy of a requirement is that every requirement has to have a unique identifier. So in this case, this is my requirement for a digital clock controller. So that is the unique string that says that is the document that the requirements are coming from. And then there is an enumeration right here that just says this is requirement number 3 of this document. So a unique requirement, usually a good thing to do is to use this term shall. A shall means, kind of frames the sentence in a very good way for writing requirements. The requirement text is the thing that describes that requirement. And as I said, it uses the word shall. And then a few optional things are you might have some coverage tags that say, is this safety critical? Does this cover a requirement from a higher level? So here's an example of a really bad requirement. So requirement 1, the DDC can be configured to any depth and width. It will have 256 words. It will support 64K bit memory with sufficient address and data. It will need some kind of reset. Also, be sure to avoid clock domain crossing issues between the CPU and memory. So there's a lot of things wrong with this requirement. The good thing is it does have a requirement, and I'm not sure exactly what this is. Is this our coverage? What is this? The problem with that requirement was there were a lot of requirements buried within that one. So here are taking that paragraph and breaking it up into 5 different requirements and framing those correctly. Lots of requirements in one was the first one. Didn't use shall. Lumped a lot of requirements together. It should be a specific requirement, not like a description of the theory of operation. Some of the things that were in there were not verifiable, like enough and very fast were words that were being used in there. You don't want to cast requirements negatively, so avoid CDC issues was a problem. And then there were a lot of things in that one. So where do we store and capture those requirements? Usually we are writing our requirements documents as like a Word document or maybe an Excel spreadsheet. That's really good because it's easy to use. There's low overhead, but generating those requirement tags is a manual process and supporting those. Another place that oftentimes people use is something like a requirements capture tool, like doors. If you're in the aerospace or in mil-aero, oftentimes doors is a requirement. And those are good because it automates those requirement IDs, it automates the revision management of those requirements and some of the tracing, but it's really hard to use. There's a high overhead. The ease of use is not necessarily there. So the question is, what is the balance between that? And so what we'd like to do is to have a tool that has the requirements stored in those Word documents or, Excel spreadsheets or whatever that are easy to use, but something that automates the process of creating and tracking those requirements. And that is where our ReqTracer tool comes into play. ReqTracer is Mentor Graphics' hardware requirements tracking tool that allows you to basically set up the hierarchy of your design. So in this case, there is a doors database that had the high-level systems requirements. But then there was a design spec that was written in Word. There was a test plan here that was written in Word. We have some design code that's written in VHDL. We've got some test bench code that was written in Verilog. We have the results database of our simulation that's going to show some of the coverage. And then we have some hardware testing text results. So what ReqTracer allows you to do is to set up this hierarchy of the documents in my design and then declare what the linkage is. So that's saying that every requirement here in this design spec needs to be referring back to a higher level requirements from our system specification. Every test that we run in our test plan needs to be testing a requirement that was done here. All the code here needs to say how each of these requirements is implemented. And then we need to say how we test each of those tests and the results. And I'll show you how this all goes as we go through. Requirements tracing, as I said, becomes this process of saying, okay, I have this requirement right here, and then this is where in my VHDL code that I actually implemented this requirement. So putting these implementation tags, that is going to create the linkage between the code and the device. And then here was my systems requirement document that I had this requirement here, and then these coverage tags are how you specify that this design spec requirement is covering this system specification. And ReqTracer becomes the hub to connect all of these different systems. So in this case, we had doors as our high-level requirements. We can bring in our Word documents. We can bring in our Excel spreadsheets, our PDF documents, whatever. ReqTracer will process those documents, create the linkage back to our requirements database. It will process my RTL code and my test bench code and create those linkages. ReqTracer can be connected to some other systems, like if you're using our pads or our Expedition board design tools, you can actually place those requirement tags within the schematics for your boards, within the constraint editor, to different constraints on your board. Our precision synthesis tool will generate requirements that are processable. And then any output logs, either from your simulation, from your board testing, you can set up ReqTracer to process those text output logs and bring that code back in. And then also the coverage database of the simulation results can be brought back into ReqTracer. And so that forms the whole hierarchy and the tracing, et cetera. And then ReqTracer can be used to generate a whole bunch of different reports. So it can generate things like coverage reports. It can generate traceability matrices from your top level down through maybe your test plan. And so all kinds of different reports that can be generated. The requirements always have an identifier. You might optionally have attributes like priority or safety critical or other things. You may be having references that reference back to a higher level, and then the description is the requirement text. And ReqTracer has a few tools to help you generate those requirements. So there is a tagger within ReqTracer that basically allows you to go into a Word document, select a set of text, and say that is a requirement. It will generate a unique identifier string. There's a coverage thing that allows you to create the coverage directories and to place attributes, et cetera, on that requirement. In this case, like right now, I have a product requirement at the highest level here. I have 5 requirements defined in there. I have a design specification where I've declared a few other requirements, and then I put in coverage directives that are saying these 2 requirements in the design spec cover this requirement from the product spec. This requirement covers here. So what this shows is that this can be a many-to-one, or this could be a one-to-many coming back. But what you need to do is right now, I only have 40% coverage of my product requirements in my design spec. So I need to figure out, what is covering these requirements. And then my design implementation, I've gone into blocks of code and I've put in implementation tags. So you can see right now I've got 60% coverage of my design spec. And then, this is not necessarily required, but what I'm seeing here is I've got this module of code and it doesn't cover any requirements for my design spec. So why is it here? That's other questions that you can ask with this. So there is a change management of requirements built in to the ReqTracer tool. So for instance, right now, I had this requirement in my design spec. It was high priority. This was the requirements text, and then I'll take a snapshot, and that'll be my alpha snapshot. And as the project is maturing, I've decided the priority of this is actually critical, and that it actually covers not only this PR number 2, but it also covers PR number 6. This isn't a great set of requirement text. Design shall be power efficient. As I said, that should probably have been something like design shall consume no more than 50 milliwatts of power or something. It should be a hard number, but you get the idea. And so now I've taken a snapshot, and at any point I can say, okay, what's the difference between my beta requirements and my alpha requirements? And it will flag anything that's changed between your different snapshots of your requirement. So that's something that's very desirable, is the ability to see how the project has been maturing. We can monitor our status. So it says we only have 60% coverage. I've got to write some more requirements to cover these two uncovered things here. You can do what's called impact analysis, and that is I have changed this requirement right here at the high level. What is that going to impact? So an impact analysis will say, if we make this change, that's going to impact these requirements at this level. That's going to impact this implemented code. So impact analysis is another good benefit of a spec, and then automated reporting, things like traceability matrices. So this is showing the traceability from my design spec down to my design implementation. So this requirement right here is implemented by these two blocks of code. And that, if I have a big hierarchy, I can trace all the way down from the top down through my document, so I can get traceability from any one level to any other. So here's, as I said, the traceability matrices. And that's basically showing that this system requirement is covered by these two design spec requirements. This system requirement is covered by this one. And so the traceability matrix shows this, and it's also showing that these other three product specifications are currently undefined where they are in the design. So ReqTracer, as I said, is sort of the hub of our safety critical design system. It is integral to our DO254 solution, which is the hardware specification for Mil-Aero. Our DO178B is the software version of the DO254. ReqTracer can be used for that as well. ISO 26262 is the automotive standard. There are similar standards for medical equipment, for banking equipment, for trains, for many different systems out there. There are very similar standards, and ReqTracer is the central hub for that. So next, I'm going to switch gears a little bit and go to, okay, now we have created our requirements document. We've created our code. We've made sure that all the requirements are met, and we've created this set of tests that we believe have covered all those requirements, but we want to do code coverage to make sure that all of our implemented code has been tested. And code coverage is really about finding the holes in your coverage. Have I executed every executable line of code? Have I branched true and false in every if statement? Have I taken every branch of all my case statements? And then there's even deeper coverage called conditional coverage. And that is if I have something like, if A or B branch true, else branch false. Now you could have a 100% branch statement. If A was true, take that statement. If A and B are false, take the false branch. That's 100% code coverage, branch coverage. But conditional coverage says, I should branch true when A is true and B is false, and I also should branch true when B is true and A is false. And so conditional coverage drills down even a little further to get that kind of coverage. So that's just code coverage. Questa, ModelSim, both of those tools will generate that code coverage report for you. And then what happens is you'll run your simulation tests, and it will say, you have not covered these lines of code. You have not taken this branch, this false branch in this if statement. You have not done this conditional coverage. Well, now the question is, do I have to write more tests to get that coverage? Can I actually get that coverage? Is this line of code coverable? Will I ever have a case where this is true? So there's all kinds of ways. Okay, this is going a little deeper. Like I said, conditional coverage, finite state machine coverage. So this is, again, the different types of coverage we can collect And and the joke is, if you have a roof, is 98% coverage of your roof sufficient? And I'd say most of us would say no, because if you have 98% coverage, when it rains, you're going to have water leaking in your house. So how do I cover those uncoverable things? What's been covered? What still needs to be covered? How long before we're done? How can I improve my process? That's the question that project managers are asking themselves, and that's what gives them headaches. And oftentimes getting that last little bit of coverage is the problem, and can take longer than getting to 98% coverage is getting that last 2% of coverage. What the challenge is when I have that 98% coverage, I have these lines of code, are those actually coverable in the system as it's implemented today? And you can spend a lot of time writing directed tests to try to get that, or if you're doing a UVM constrained random test bench, playing around with your constraints, trying to hit those last few uncoverable items, and that can lead to a lot of time. And so what often happens is we run our test suite, we collect all the coverage information, we look at that, and then we have to manually make decisions and say, you know what, I think those lines are uncoverable because this is a reusable block of code, and the way that I've configured it through my generics or parameters or whatever, those lines of code are unreachable. And so I'll write some manual waivers, and I'll create, this waiver statement for my coverage. Or you say, well, I think those lines of code are coverable, so let me write some more tests trying to cover those. Let's rerun let's run those tests. Let's merge that into my database and see if I've covered those. What our Covercheck, which is a formal verification tool, does is you run your verification suite. You collect all that coverage information. You have those coverage holes, and then once the Covercheck will do finite state space analysis on your design, and it will find the lines of code, the conditions, the whatever, that are uncoverable. It will detect that they are uncoverable, and it will say, these lines are uncoverable because of the way you have configured this. And it will write those waivers for you, and it will generate, all of that for you so that you can go forward. Do you actually go to code line level into modules, assuming C language or M files? So Questa does not do C code coverage, but it does RTL, VHDL, and Verilog coverage. And yes, it actually goes that low into it. So another question was how ReqTracer and HDL Designer can be used effectively to comply with DO254. And that's kind of, what we were saying is that by having the requirements tracing, that helps you to create the artifacts that you're going to need for your DO254 auditor. Anyway, let's get back to here. The other possibility is that you will run your code coverage, and Covercheck will find and help you to create the tests. So if it says this line of code is coverable, it will show you a waveform that will help you meet that coverage. So as I say, you run your test bench, you get your coverage results. Covercheck will create exclusions for unreachable lines, and then it will create witness waveforms that say, if you apply this stimulus, that will cover this line of code that is currently not covered. And so it gives you a hint on how to create a new test that will cover that. You put both of those things back into your design. You run those tests. You do those coverages. You look at the coverage again, and you should have eliminated more and more lines of code. And you just iterate on that until you've either covered all the lines of code or given exclusions and reasons why you cannot get coverage on these things. That's pretty much what Covercheck will do for you. It helps you to reach all of those unreachable lines of code. We often see that people, when they have uncovered code, they will spend a lot of time trying to either come up with exclusions or generate tests that will cover those. And we believe that Covercheck helps to get to that 100% coverage much quicker and will pay for itself in a single project. SecureCheck is asking the question of, does my hardware have backdoor paths that will allow someone to hack into them? So for instance, in the automotive world, the CAN bus, is there a way for someone to get in through a backdoor and, take control of your vehicle? There was actually a study done that some hackers were able to hack into through the radio of a Jeep Cherokee and were able to apply the brakes or disable the brakes or mess with the steering. And that's, an undesirable thing to happen. Mobile banking, big problems with someone hacking into mobile apps and being able to access your checking account, et cetera. And, oftentimes that can be through software, but sometimes that software hacking is allowed through hardware paths. And then this is kind of the joke that in the future, with the Internet of Things, you're going to have, people hacking into your smart trash can and demanding a ransom so that you can throw something away, or saying that your vacuum cleaner is going to blow dirt all over the place, or your coffee machine, or whatever. How do we prevent that? And then another thing in the safety critical world is things that should never happen at the same time. So in this case, it wasn't necessarily a hacker, but this is putting the flaps up on the airplane at the same time that you're, activating the air braking on that airplane. Probably should never happen. We want to make sure that that doesn't happen. And so the root of all of this is down here at the hardware level. And so how can we protect against that hacking at the hardware level? And we do that with our formal app called SecureCheck. And so with SecureCheck, what happens is, maybe I've got this system here and it's got an encryption engine. So I don't know if it's a banking system or whatever, but I've declared that, I know for a fact that I should be able to write the encryption keys through the microprocessor interface right here. And then that encryption engine will be able to access those keys and decrypt things via this path. So I've declared that these two paths here are my legal paths of access to my encryption keys, but then SecureCheck will go through and it will do a hardware state space analysis. And in this case, it's discovered that through my AXI bus, there is this backdoor path to be able to get access to those encryption keys. And also maybe through my PHY, through my Ethernet, there's another path where I could even read and write those. And so SecureCheck is all about declaring the legal paths and then making sure that there is no way for any other process to get a hold of my protected data in my system. So the formal solution is exhaustive. So trying to do this manually is quite difficult. You can white hat hack all you want, but by doing this formal mathematical exhaustive process, it is a much safer way to make sure there are no backdoor paths into your confidential, secure sections of your design. A few cases here, a consumer electronics maker, they had a consumer electronics entertainment system, a gaming system I might put out there, and their product ran into some hacks where black hat hackers were doing denial of service attacks. They found they had these issues and they were trying to do manual methods to find all the backdoor paths. That didn't scale very well. They were looking at with some other software solutions. There were paths that they were missing. Our competitors' formal solutions were running very slow. And so they applied SecureCheck. They found unexpected paths that were not found by any other tools. The analysis was very quick, and they were able to repair those. So as I say, what the SecureCheck is all about finding sneak paths in your hardware, identifying those before the chip is created, and fixing them before manufacturing the device. So I'm going to talk real quickly about clock domain crossing. So clock domain clocking has become probably the second most important issue in the reason for most ASIC respins. So we can see functional logical bugs is the number one. So that's misdesign. That's, doing good verification. Power consumption is another one that's up there, and that was on the rise in 2016. I think I have some 2018 data that shows that's come down a little bit again, but clocking issues continue to be a big issue in the ASIC world. And we're also seeing that they are the second leading cause for needing to respin your FPGA. And so that is clocking issues, and generally it is asynchronous clock domain crossing issues. So asynchronous clock domain, every time you cross from one clock domain to another, you have the potential for metastability. So when a signal goes from one clock to another clock domain, even if these have nominally the same frequency, maybe this one is 10.00001 and this is 9.99999, that means that these clocks are drifting with respect to each other, and eventually you will have a setup and hold violation on this register. And that causes this RX to go metastable, which can then go into your logic and cause lots of issues. So our Questa CDC product, what it does is it does three things. It, first of all, identifies all paths that cross from one clock domain to another. Second of all, it checks whether or not there are synchronizers in place and whether those synchronizers are appropriate type of synchronizers. Third, actually, I guess it does four things. Third, it checks whether or not, even though the synchronizer is there and it is the correct type of synchronizer, whether the timing protocol that that synchronizer is using is actually being violated. And then last of all, it does CDC reconvergence. And so it identifies things that are definitely violations. It identifies things that are definitely safe. And then it also identifies things that it says, it looks okay, but there's a caution on here that maybe you need to run some simulation to either bump this up to a pass or identify that it is a fail. So these violations are going to be things like this, where it is structurally, there is no synchronizer here, or this is actually a synchronizer, but you have combinational logic between this register and the synchronizer. So these are structural violations that it identifies immediately with its static checking. The second thing is the cautions that it's pointing out here are something like this, where it's saying, okay, I'm trying to pass a bus across, and this is a proper structure. I'm passing a signal that says go ahead and sample. This is being held stable. Go ahead and sample it, get it in there. Okay, it's crossed over. But this has a timing protocol which must be obeyed, and that is you better hold this static for the entire time it takes to generate this sample, and for that sample to go away, get synchronized over into this domain, and then turn the sampling off. this signal better not change for that entire amount of time. And so that is the protocol checking that it does. And it can do that protocol checking either with that formal state space engine, or you can bring in your test bench and it will use your test bench stimulus to either promote or demote those things. The last piece is what's called reconvergence. And this is the trickiest of the CDC problems. So right here, you have a signal that is in this domain. I have properly synchronized it over into the green domain, and then I've done the same thing here. I've got a signal, I've properly synchronized it over into the green domain, but then you'll see that those signals, they go through some logic, they eventually come back together through some logic cone. And the question is, these signals had a certain timing relation. Maybe they were generated on the same clock edge, and because of this synchronizer, they can now be plus or minus one cycle out of phase with each other. And so when they come back together through this logic cone, does that cause a problem? And so we automatically defined all the places where metastability could occur, and then find all the reconvergence paths, and then inject jitter into your design to try to identify whether you have problems there. And we are currently the only CDC tool that has gotten ISO 26262 certification. So of all the CDC tools on the market, ISO 262 has given no one else this certificate that it is a complete CDC solution. And we got that in about 2016 on the CDC tools. No one else has still gotten that. And then the rest of our tools, our SecureCheck, et cetera, all got ISO 262 certification at the end of last year. So we are the only formal tool set on the market with ISO 262 certification. So anyway, CDC is all about finding those clock domain crossing issues. And again, that is one of the biggest drivers of unsafe designs. And so it's just another piece of our safety critical puzzle. So that is the webinar. Thanks, everyone.